I started out in the military. I studied computer science back in the day and immediately lost all of that knowledge of data structures and algorithms as they taught me how to crawl through the woods and shoot tanks. But towards the end of my tour, I had the privilege of being part of the cyber mission force for the latter 3 years. And in the 6 years since I have gotten out of the Army, I've been involved in a matter of security research, training content development for practitioners, and most recently just doing a lot of malware analysis and detection engineering with Trinity Cyber, which is, I was able to join an awesome team, and they've produced a solution called full content inspection, which at network speeds just parses and scans entire sessions of traffic between a trusted client and the internet, and through that we're able to make some really fine-grained context-aware detections of exploitation attempts, malware, and pull those out of the session before it ever makes it back to a vulnerable server or an unsuspecting user who just clicked a link. So it's been great being a part of that team, and as soon as I got on board, I had to learn how to deal with this problem of like writing a regular expression to describe something that may not appear in the context that I initially see it, and I have to imagine what else that looks like. So I've been using that skill set for the 2.5 years I've been a part of that team. So this is the overview for what we're going to be talking about today. Basically show you who, what, when, where, why, regular expressions, talk about some of this basic syntax, and then some of the pitfalls, including the biggest vulnerability that may exist if you're incorporating this into your applications, which is RDOS, and some of the applications for a cybersecurity blue team, and hopefully demo some of those for you as well. So overview, I think this encapsulated it well. Regular expressions are terribly awkward and extremely useful, and depending on your exposure and usage of them, you exist somewhere on that continuity. Maybe in both cases, maybe they're still awkward and also useful, but hopefully we push a little bit more in the usefulness direction today. I included definitions from both Linux and Microsoft sides of the aisle just to anger all of the practitioners, but I like a little bit of both of these. The top definition highlights that it's a search pattern. Like, that's what you're trying to do. You're trying to find the data somewhere. And in the bottom definition, I like how it breaks that out into character literals, operators, and constructs, and we'll explain a few of what those are. The answer to what implementations exist today is all of them, and basically as many different types of applications, languages, and implementations that you could find. There's probably some nuance that's different from the way that you used it before. Perl-compatible Regular Expressions, or PCRE, is one of the earliest and most popular implementations, and much of the syntax is similar to or derives from that, and so that's what you're going to see in today's talk. Why do we use regular expressions? At the end of the day, most fundamentally, it's to find a match. But it's more than just finding it. After you find the match, it's to do something with that. Usually it's going to be to return documents or records if the regular expression is to search in a database or a table or a seam. It could be to extract data, so after finding the match, finding some portion of the match, pulling it out and doing something with it. Search and replace. So again, once you find a match, either all of or a portion of that, replacing it with something different. And it could be to validate or invalidate input. So a match might say this is acceptable, or a match might say that no, this is something malicious or improperly formed, and I don't want to accept that input. So again, it consists of literals, wildcards, anchors, classes, groups, alternation, quantifiers, and escapes, and a couple more advanced syntax that I'll explain at the end as well. So a literal is exactly that. You type the characters and you want to find exactly those characters. The example I have here, TVQQ, is the base 64 encoded form of the magic bytes, or initial bytes of a Windows executable or portable executable file. So basically MZ and some null bytes is what you're going to find at the beginning of every EXE. And we often see this base 64 encoded form of it in malicious scripts, like a PowerShell script where a malware actor is essentially base 64 encoding the entire thing, dropping it in the script, and when a user executes it, it writes it to disk somewhere and either sets a scheduled task or it executes it immediately. But basically, if we see those literal characters in some type of script, JavaScript, batch file, etc., usually it's bad. And for those who just want to know what it is, the bottom one is some random data. base64 encoded. So wildcards. This is represented by a dot or period. This is a pretty naive way. In fact, most of these examples, there's probably a way to do it better, but I want to illustrate one form of syntax at a time. But a pretty naive way of finding variations of the word password. So if you are, a red teamer looking for variations of passwords somewhere on disk, and you're searching through config files, text files, my information.txt on desktop or whatever, then you might use this regular expression, and you would find both forms, password and password with some like LEET-coded replacements. But again, since it's still have some literal characters in there, it wouldn't match these bottom forms of it. Anchors restrict where a match may begin or end. So the caret means that the start of my expression is going to be the start of input. Now, that is going to be context sensitive. So your start of input could be the beginning of a file that you're scanning. It could be the beginning of the line of text. It could be the beginning of a field that you've extracted with your application and submitted to the regex. So it depends on what the input looks like, but essentially beginning of input is what the caret anchor signifies. And again, MZ, magic bytes for Windows executable. $ would be end of input. So in this particular example, I want to match a file extension. So .php $ means that I have to find at the end of input. So if my entire input is a file name, then this would match that. Notably, if you add something else like PHP5, like yes, that would be a valid file extension, but it doesn't match that regular expression. There's ways that it can, which we'll show later, but that's what an anchor is. Classes match any character literal inside of the class. So in this particular example, I want to find both the uppercase and or the lowercase form of IEX, which is a PowerShell alias for invoke expression. Again, a type of obfuscation that we see frequently is threat actors will change the casing of something like this, which PowerShell would accept as valid, but if someone's just looking for a case-sensitive form of it, they might miss. And notably, it has to be those specific characters, which is why it doesn't match the bottom. And then something that you'll see is increasingly useful is the negative of a character class. So in this particular case, I want to find anything that's not inside of there. If you wanted to do a very particular typo squatting regular expression, where it's I want to find where someone's replacing the L in Google with something else, literally anything else, I don't care, then this is an expression that you might use. And it'll find when the Google is replaced with a 1. This is a shorthand for many common character classes. So frequently people want to find digits, or they want to find all the word characters or all the white space. And doing \D, W, or S is just a simpler way to write it instead of every single time writing out the entire character class. It's worth noting, as you see in the examples of what those character classes actually represent, that you can designate a range inside of the character class. So 0-9 is everything from 0 to 9. This is important because if you want a literal hyphen inside of your class, then you need to escape it. Otherwise, you'll think I'm going to do 9, a hyphen, and A, and find one of those. And in reality, you're looking for everything from 9 to A. So you have to be careful about that. And the uppercase forms of those letters are, again, those negative character classes. So uppercase \S would be anything that's not white space. Groups match the entirety of a subpattern that is within those parentheses. So while character classes are really used for saying, I want any of these particular character at this character position, a group is useful for saying, at this position, I want to match the entirety of what's inside of these parentheses from this point forward until the match is complete, and then it continues to evaluate the expression. If you just have parentheses all by themselves, then that is what we call a capturing group. You might recall earlier when it's what are we using it for? Sometimes we want to grab a piece of data and do something with it later. Capturing groups are what we use that for. So in the example on screen, if I know that I'm going to see login ID equals some number in, let's say, a log file, and I want to find all of those numbers, then I might write a regular expression in which I match on login ID equals some number, but all I want to return is all those captured numbers. Oh, by the way, the question mark =sign at the beginning of that parentheses is what we call a non-capturing group. That's when I just want to logically group these characters together, but I don't need to keep it for later. Alternation inside of those groups shows like different paths that the expression could take. So if I wanted to find www.google.com or bing.com, but I don't want to try using character classes to represent that because I could end up with a really weird mishmash, then I can use alternation within the group in order to accomplish that task. And then we have quantifiers. Quantifiers specify how many of a particular character or a particular group that we want to find in our match. We'll start with asterisk. Asterisk simply means 0 or more. So we have a sort of like a function call here in which we've got the word function, open parentheses, 0 or more word characters, and then a closing parentheses. And you'll see what it matches on here. And note, because I didn't include a comma or a space in my character class, then it won't match on the bottom example. But this is 0 or more. A plus means I want to find one or more of that group or that class, group, or character. So if I just want to match on literally any variable name, then I can use /w plus. And you'll see that it doesn't match on the malformed code in the bottom where there is no variable name. Also, this, by the way, is why underscore is in the word character class. Because back in the 90s, Perl programmers said we want to include this because we want to be able to use like a single shorthand to match any variable names. So that's why the underscore is in there. Hyphen is not, though. Don't ask me why. And then we have question mark, which basically means 0 or 1. So if I wanted to match both the secure and unsecure form of HTTP protocol, then I can use S question mark to say it can be there or it cannot. And then braces can be used to discretely quantify how many of that construct that I want to find. So if I wanted to represent a phone number, I can say 3 digits, and 4 digits separated by hyphens. Obviously, that wouldn't match the social security number format because that's 2 in the middle. But this is helpful when it's going to be a specific number or even a range. If you have 2 numbers separated by a comma, then I'm going to say I want to find at least 3 and up to 5 of this particular character. And then I'm going to very briefly touch on this because I feel like it's a little bit more advanced. But you can also describe the behavior in which you're going to find the repetition. By default, regular expressions are greedy. So if you say, I want 1 or more, it's going to find as many as it can in the match. However, if you want to find only enough before it continues with the remainder of your match, then you can do what's called a lazy quantifier. Use a question mark to signify that. And I try to do an example here. Greedy, laziness, that's going to matter a lot more as we talk about redos later. But I want to at least mention it so you've heard the terms. And then possessive, keep in mind the term backtracking. But basically possessive is like greedy, which means it's going to find as many valid, consume as many characters as it can in the match. And then if it gets to the end and it's not able to continue, then that's too bad. It doesn't backtrack and try to find a match after that. And finally, escape. It's kind of hard to do the other examples without already having escapes in there. But you may have noticed if one of these meta characters is I'm trying to find literally, then I do have to escape it so the regular expression realizes, oh, I want to find the actual bracket and I'm not creating a class in my expression. These are all those special characters or meta characters that need to be escaped. Hyphen, as you see at the bottom, it needs to be escaped inside of a class. If you just find it and elsewhere in your expression, then you can escape it or not. These are some of those advanced syntax. You can do some mode modifiers or flags within or around your entire expression. You name groups, back references, look aheads, look behinds, conditionals. I'm not going to spend any time describing these, but we can definitely have a conversation afterwards if that's interesting to you. But it's basically ways of adding a little bit more complexity to the regular expression. And notably, it's not supported in every implementation, which we've already described. This is also a screenshot of a quick reference from Regex 101. So basically the things that I've talked about, classically, the joke is, well, I'll learn regular expressions the next time I have to use it, and then I'll forget about it, and I'll learn it the next time I have to use it. Something like this, a cheat sheet, is really useful when you're having to create something on the fly and you don't remember everything. They exist everywhere, and especially in the really popular tools. So putting this into practice. This is my favorite, my tool of choice. I think it's really powerful. Mostly I like the giant test string section of here because I can just put a lot of data in there and do a lot of different test cases. But basically any tool most tools that you use are gonna have all the same features. This is just my tool of choice. Regexer is another one. I particularly like just the UI for how they like do the description of everything that's in the expression that you're writing. So if like you're kind of like new to regular expressions or just trying it out, I think that can be just more helpful. I think it's just bigger, more intuitive. Regexpert is a really cool tool. You've seen all the visualizations that I've been putting alongside my examples, and it can create those, out of whatever regular expression you're using. So I think this is useful if you're a really visual learner. It's like I just need to get my head around like what are the possible paths that it's taking. And then DebugX, it's like kind of an all of the above. It's got a visual element, it's got a debugger element, it's got a place for you to put test data. So again, if you are more of a visual person, then this might be useful for you. So, simple example. How do we match an IP address? Any initial guesses? A pretty basic, guess would be, okay, let's find some numbers, one or more numbers, and separate them by periods. However, recall, it can be 1 to infinity, like 1 or more. And this can be a bit problematic because that's not what we're looking for. So let's try to describe it a little bit more discreetly. We could say 1, 2, 3 numbers separated by periods. Also, you notice the /b character in there, which I forgot to explain earlier. This is a very special character class, which basically means anything that's not a word, but it doesn't consume a character in your expression. So the not a word thing could be beginning of input, and this would still successfully match. So this gets us close, but as you see down where I'm describing things that don't match or should not match, it is still matching on because it's describing the form that I'm looking for, but that's not a valid IP address. So it's one of the things that you have to consider as you're creating these regular expressions is that not just like, okay, what does it look like structurally, but what are the actual bytes going to be as I come across them? Because I can't stop in the middle of our regular expression and say, oh, I found 1 to 3 digits. Let me throw it over here and do some math and see if it's less than or equal to 255. I simply can't do that. So I have to imagine like what is the data going to look like character by character as I come across it. So we can do a little bit better. I have to imagine what is it going to look like if I find 1 character, if I find 2 characters, if I find 3 characters, and what happens if it's a 1 followed by 2, a 2 followed by 2, if it's a 4, I got to do something with it, if it's a 5, I got to do something with it, if it's 2, 6, I got to throw it out. And so this is getting closer. I mean, and this is basically the solution. So how well does AI do this? And this is the only time I'm going to talk about AI in the talk. When I was first putting this together in 2024, AI came up with the trivial solution. And when I gave it some feedback, like, no, there's a test case that matches your regular expression, but it's invalid, then it got closer to the truth, which was good. In 2025, it still shows you the trivial solution up front. And then in its explanation, as it talks about caveats, like, oh yeah, by the way, none of those are valid octets, so here's the right solution. And I had a great conversation at last night's meetup about AI and creating regular expressions that I thought would be really helpful. It can create them if successfully, if one of 2 conditions are present. One, it's seen it before. So if it exists in published material, Stack Overflow, code bases, and it was done properly the first time, then there's a really good chance that you can produce something useful. If you say, like, write me a regular expression that, detects an IP address. The other situation is if you can adequately, fully describe the input that you want to match on and any variation to that input, and those variations are not too different from each other, and at least part of that has been done before. Like, for example, matching a for loop and then some data and then, the end of the for loop. Like, AI can basically get to a successful solution. You may still have to tweak it after that. I think it is going to get better, But what I have found is I'm trying to like find some malicious code and then an obfuscation of that malicious code, and then where they change the order of some of the elements, that it just starts to hallucinate the solution. It's hard to get something useful out of it. But I think it's going to improve. So here are some cautions. First is a question on efficiency. Any thoughts? This is one we used before, IEX, case sensitive. And then I threw a variation of it, like find IEX or IWR. And any thoughts on which one would be the more efficient expression? Anyone A? B? So the answer is B. And I did throw like the worst case scenario when comparing A to possible input, just to illustrate the point. The beginning character is where the expression is going to evaluate, like, okay, should I look for the rest of the match? And when it's one possibility, then it's going to go until it finds lowercase I, and then evaluate the rest of the match. And you know what? The first time it finds it, it may not successfully, find the rest of the match. But the point is that in A, there's two ways in which it's going to start to evaluate the rest of the match. When you're talking about something like a single field name, right, and like I want to run my regular expression against like, is this a valid email address or not, then this matters much less. But when we're talking about thousands, millions of requests that it's evaluating against, or megabytes, gigabytes of data that it's running across, this is when efficiency starts to make a difference. So you just have to make a design choice, like, do I need this to be more efficient, or do I need this to be more flexible? These are some other common pitfalls that you might fall into. One is overcomplicating. I find that it's useful to start with the simplest possible case and write the expression for that, and then start to add some complexity. Because if you try to overcomplicate it from the start, you're going to like add things in that you don't really need, and you're going to start to like make the expression go down paths that you never really intended. Failing to escape meta characters, I found is pretty common, especially if you're like copying and pasting some input into the regular expression, and then you start to escape things, but then you miss something. Not testing thoroughly. You notice that when I was looking for, does this match a valid IP address, I had what I wanted to match on, but then I also had what are all the things that I don't want to match on, and be creative as you're developing the regular expression. Like, don't just say like, okay, yeah, this is clearly invalid, but also like, this is close to valid, and maybe if I throw like this character in here, it shouldn't match. And then you realize that your expression still matches it, and now you have something that you want to mitigate. And then this is just going to come with experience, but not understanding the nuances. So laziness and greediness is one of those. The first time I ever gave this talk, I actually still didn't understand that properly, and I answered a question incorrectly. Classes, again, not escaping the hyphen, or adding things in that you don't realize are there. It's like, well, I want to match on every word character, but you don't understand the underscores there. And then what supported behaviors or syntax is in what I am using right now. Like, for example, in YARA, which is a type of malware matching technology that I'll show later on, you can't use non-capturing groups. It's just not supported. If you try to put it in there, it's going to throw an error. So things like that. Those are the nuances of using it that you're really going to gain from experience. But I always recommend, if like you're going to spend some time doing it in your language platform, whatever of choice, read the manual on those regular expressions. I think it'll give you a lot of mileage. And I think this is a cool quote. Regular expressions can be used for great good, but is frequently the source of a lot of problems in today's technologies. So what are the stakes? What happens if this is done poorly? First of all, broken, bypassed functionality, like if you're using regular expressions for some form of authentication or validating input, and you miss something. Like, this is why WAF bypasses exist. People are trying to smuggle something bad past a web application firewall, and they're, for the most part, using regular expressions to find the bad thing and strip it out before it gets to the back end. And the reason bypasses exist is because usually, given enough time, you can find a way to fool the regular expression into accepting your input. Inefficient resource usage, we touched on that a little bit with efficiency, but that can be extrapolated into a denial of service, which is something we'll discuss soon. And then in my line of work, if I'm writing the regular expression poorly and I miss a potential malicious case that just isn't matching, then we have missed alerts. Something can get through to the client, potentially even malware would evade detection. So this is an example in the real world where this caused problems, or at least potentially caused problems. In late 2020, the Facebook JavaScript SDK, it included these lines of code. There was a regular expression that was designed to match on a domain, basically only allow communications from facebook.com and its subdomains. And then inside of an event listener, cross origin messages were tested against this domain, and if it matched, then that communication was accepted, and if it didn't, then the function would just return. Anyone see the problem with it? Yeah. They don't have a period in front of facebook.com. So its check is designed to make sure that only facebook.com and its valid subdomains pass and literally anything else fails, but evilfacebook.com would pass. So the impact for this is if an evil domain was able to create an iframe of vulnerable web applications that included this SDK in its code, even if only to implement the sharing functionality, then by forcing request to facebook.com, then they could, and reading the location property of those iframes, if a user happened to be logged in to one of those vulnerable applications, then an attacker could leak sensitive data like OAuth tokens or other sensitive information that would allow for full account takeover. So Facebook paid $10,000 because they missed 2 characters. Thankfully, this was never exploited in the wild, but it would have been very serious if it was able to be. But also extremely serious is not just attacking users one by one, but shutting down a service or application so it's unusable by everybody. Regular expression denial of service is an attack on the availability component of the CIA triad, which is just a framework that security personnel use to describe what's important in application: confidentiality, integrity, and availability. And causing downtime because a malicious input is consuming an oversized amount of system resources is going to attack availability. This is because most, not all, but most regular expression engines are built on top of non-deterministic finite automata. And because backtracking is a valid behavior within these engines, then when you can craft input that consumes too many cycles, then it will backtrack catastrophically and hang for minutes, hours, days. This is an example of what that looks like. This is from OWASP, the Open Web Application Security Association, and it's describing a potentially vulnerable regular expression, which is basically recursively looking for A's. And for an input that is AAAX, there are 16 possible paths for this finite state machine to evaluate that input before ultimately deciding that it will never match on this. And that's important to distinct. REDOS is made possible when an expression fails to match. If it successfully matches, it still goes relatively quickly. It's when it fails to matches that it continues to consume cycles trying to do so. If you go from 4 to 16 A's, there are over 65,000 possible paths that this state machine can take before ultimately realizing that the match will never exist. This is a visual representation of that backtracking principle. So if this, algorithm trying to find a way out of the maze is our regular expression, then it's going to consume characters in a successful match. And then when a character may be consumed two or more ways, then it'll just take one of those directions. And if it reaches an end of input or a bad character that fails to match, then it's just going to back up to the last saved state. Like if you're a gamer and you save the game, well, the last time I had an opportunity to go right or go left, I'm just going to revert to that and go left instead. And essentially that's what the algorithm is doing. And when it's 1 or 2 possible diversions, that's not going to take up a lot of time. But when every single character can possibly divert, then you run into exponential time to try and solve it and eventually fail. So as an example, this is the regular expression describing a valid email address according to like the RFC standard, which nobody uses for obvious reasons. So we tend to find shortcuts, like how can we describe an email a little more intuitively and in a way that like someone could maintain if it ever changed. So a company called Superhuman, in a blog that they published about denial of service with regular expressions, described how they ran into this problem. They were trying to describe an email address because their application would find them and like automatically convert them to mail-to links. And their original expression was anything that's not an @ symbol, 0 more of those, then an @ symbol, and then 0 more @ symbols. That was their original expression. And they realized, oh wait, it could be inside of quotes and still be a valid address. I don't know why that's the design choice that they made as the first alternative, but they decided to throw in there, okay, stuff inside of quotes or anything that's not an @ symbol, and then find the @ symbol. According to this regex, these are all valid email addresses, which is really interesting. And I'd like to note that any match inside of that group can repeat. So you could find the match in which there's stuff inside of quotes. And then in the next group you could find stuff that's not an @ symbol. And in the next group you could find stuff that's inside of quotes. And then the rest of it. But what if it's all quotes? So in this case, it's going to evaluate 1/2 of that alternation, and then it's going to evaluate the quotes that way again, and then it's going to fail to find an @ symbol, and then it's going to start backtracking. It's like, oh, let me try again. And then it's going to consume that same quote a different way, and it's going to fail. And it's like, oh, let me try that again. And it's just going to keep backtracking. And the worst part of this is, once it gets to the beginning, it's going to say, well, I just wasn't able to do it anywhere from there. It's going to step 1 character position forward and repeat that entire process. With 4 quotes, it takes over 100 steps to realize that it's never going to find a match. With 40 quotes, it takes over 100,000 steps and 3 seconds of like actual runtime. If I add a couple more quotes, that goes into 5 minutes. I double it, that goes into like 5 hours. That the system simply doesn't respond. In a 2018 study of RDoS, some researchers described these as superlinear regexes, basically RDoS vulnerable ones. And they found multiple examples of those in publicly available maintained NPM repositories. And common patterns that you'll see is a character that's repeated 1, 0 or more times, and then an optional character, and then that same character repeated 1 or more times. And so essentially, whatever that character is, let's call it A, could be found as many times as possible, and then found again, and then fail to match. And it starts to backtrack and just reevaluate it all the ways on both sides of that equation. And this resulted in some very public downtime. In 2016, Stack Overflow experienced this in an outage for 34 minutes. The reason this is the case is it was basically trying to trim white space. The problem was that if you have multiple megabytes of white space in a file, then it's going to start at the beginning of that white space and go all the way to the end. And if there's no white space at the end, it's like, oh, failed to match. Well, let me go back to the beginning, step forward 1 position, and try again. And essentially, if you think of like an arithmetic series, the sum of that arithmetic series, that's how many steps that it was taking to fail to find a match using that regular expression. In 2019, Cloudflare went down for the same thing. I tried to highlight it because it's kind of a complicated expression, but basically, if you found a bunch of pluses or minuses in a row and never found an equal sign at the end, then that was how you could exploit this. And it went down for 27 minutes because of this expression. And it's not just your own applications that you have to check. If you imported Python multipart in one of your applications before mid-2024, there was one of these vulnerabilities in the content type header. And this is where I want to highlight the importance of peer review, because this is the expression that was used, and whoever wrote this just fat-fingered an extra backslash. And instead of finding an escaped period, they found a backslash and any character. That's a wild card. And on the other side of that alternation, that's anything that's not a quotation. So essentially, there were 3 different ways, 3 divergences at that position in the expression at which it could read a backslash into the match. So if you just had a bunch of backslashes and you never followed it by a quote, which is the last character in that expression, then you could consume 100% CPU, which is exactly what they did. This is a write-up that was posted by vSociety. So how do we prevent these? First of all, don't try to replace robust functionality with something that you built yourself. Just like there's the classic saying, don't roll your own crypto, like don't write your own regular expressions. If there's a way to parse headers and it's publicly available, like I went and looked at like the Git commit, and that's essentially what they did, is they just replaced it with functionality that already existed that was robust and peer reviewed by many more people. But if you are writing your own, ensure there's only one way to match a string. Minimize the possibility of those divergences. One of the ways that's useful for this, especially when you're describing like a lot of alternations inside of groups, is have a boundary character. So if we think of that initial example, like A+, and that group can be 1 or more times. Well, if you just threw a boundary character in there, like B, and then 1 or more A's, and that group multiple times, that expression is no longer vulnerable to a redos, because there's a boundary character. There's a way for the inside to fail, and you don't get this like multiple quantification. Test on exhaustive worst cases. And this goes back to the testing comment from earlier, but try to find all the ways in which this could go really badly. Just imagine those and make those part of your test cases that you do not want to match on. There are a number of online and offline writing tools that help you check expressions that you build for this problem. And then peer or subject matter expert review. Here are some of those tools. I found regex.rip as I was like preparing this talk, and I thought that was really useful. What it does in the background is it turns your regular expression into that NFA, and it does some analysis on that graph and tries to find loops within it, which I think is really cool. And actually, it'll show you an example of input that would cause a vulnerable expression to fail, which is really useful. Redos Hunter, Regex Buddy, those are both offline versions that can also examine your expressions. So here's some practical applications. Within the cybersecurity world, which is again, is my context, searching logs, creating alerts, which is similar to what I do. We create detections and responses for them. Analyzing malware, so finding particular strings that are common in malware, or function definitions. Writing YARA rules, which is a subset of that. Code review. So if you know what bad looks like, then you can write a pattern to describe it and potentially like search through repositories and catch problems before they get pushed to live. And then, like I said, with most of the applications that you're using which have some type of search functionality, there's usually a way to implement that. You might have to dig into the documentation for that. But like if you're using a seam, I guarantee that there's a way to write a regex to search through the fields within that seam. And then you can throw it into your scripts. And I'll show an example of that at the end. So demo time. Obviously, we don't expect the demo gods to shine well on us. So I've got most of these canned, to be honest, but the last one I'll do live. So, as I think Matt earlier in the day already spoiled, if you use grep, you're already using regular expressions. Congrats. For this example, I pulled a data set from a cyber defense competition back in 2012 because it just had a huge HTTP log that I thought was useful, which I found at that URL address. And it's a 1.3 gigabyte file. It's got over 2 million lines in it. It's just your classic, origin, destination, HTTP verb, URL. It's got like user agent string in there. Sorry for those who got used to my dark theme and got blinded. So if I was to say like be on incident response and I suspected that on this particular web server that someone had used SQL injection in order to achieve code execution, exfiltrate data, etc. And I just wanted to find SQL queries in the code and I just used grep, then I'm going to find 2,500 occurrences of that, which is doable, but that's a lot to sort through. So maybe I want to find a way to describe that a little bit more specifically. So this is what I came up with. I wanted to find an injection character, which is going to be your single quote, double quote. I included URL forms of that, encoded forms of that, even though after looking at the data I realized, well, it's pretty much normalized. But finding injection character, and by the way, harkening back to a different part of my talk, this is where I kind of made the choice to throw away efficiency for just flexibility within the regular expression. So then I wanted to find anything that was like, not an ampersand, because I didn't want to move into a different URL parameter. And then I wanted to find evidence of a SQL query. I chose select. You could also choose union, concat, whatever. You could even create a group and throw a number of those terms in there. But for simplicity's sake, I was looking for one. And then I want to make sure that I don't enter a different URL parameter or a different line of the log. And then I want to find a SQL comment. Like I want to see that like, okay, yes, this is intentional. It's not just someone fat-fingered, like they're trying to do an injection and exit it cleanly. And so I run this query and I reduced my data set to about 250 lines instead, which is awesome. And then if you want to do the same thing with grep, what I used here is TAC-E. If you've ever used egrep, it's basically the same thing, but that's been deprecated in favor of using the TAC-E flag with normal grep. And I use TAC-O just to show like the matches themselves. And if you want to see what that looks like, my hypothesis is someone just ran SQL map against this server, because it's mostly just random numbers. So, most trivial example, if you're using grep, you can use regular expressions. The second example is showing you how to use it in YARA rules. A lot of what I do is detecting obfuscation itself. Because threat actors are really smart and they found very creative ways to hide the actual malicious code. But usually the methods that they use to hide it are themselves detectable. And so that's what I tend to target. So the context here is specifically an XOR encrypted payload and detecting the XOR deobfuscation routine. We see this a lot in JavaScript malware. I've seen it in like HTA files that are inside of archives, that are inside of emails, or embedded as like injected scripts on like WordPress sites that are vulnerable to some sort of code injection. It's like a frequent use case. We've seen it in a number of other ways as well. But if I'm like looking within my particular script context engine, which is something I've got available in the platform that I write in, then I want to find this XOR decryption routine. And oftentimes it looks something like this. So this is an example that I just basically pulled down from VirusTotal. So I don't know where this was originally seen, but you can see that there's this encrypted payload. And I'm never going to be able to get at that unless I have something that's like analyzing memory in runtime. And I think I have a better way to detect it, and that's to target this loop up here. And again, like I said earlier, this is one of those cases where if I just sent a couple examples of this to ChatGPT and said like, write me a regular expression that detects this, I got something pretty close that was pretty useful. But the problem is when they also make that exact same routine look something like this. And then I have a problem, because I have a more complicated use case. So this is what I'm coming up with. So this is my regular expression to detect that XOR decryption routine with some flexibility for the ways in which the data will appear. As I start to break this down, I want to find the opening of the for loop. I want to find the counter declaration, and I used let in here. Sometimes you're also going to see const var. So that's a way that this could be improved, made more flexible. And then a lot of times we'll see either a hexadecimal representation of an integer and maybe some math thrown in there as well, which is why you'll see like the arithmetic operators. Next thing, I want to find the exit condition. That's usually based on length and an increment counter. And then I want to find the end of that conditional declaration and the beginning of the loop logic. And here's where I'm matching on that. This is that simpler version of it, and then that more complex variation using Regex 101. And this is the second half of the expression. I want to find a variable appending more data to it with each iteration of the loop. Usually this is a variable that's just declared as a blank string before the loop starts. The variable name's not important to me. There are some types of detections that do like try to grab the variable name and then find it later and do a back reference to it. And I find that like if you target the right thing, then just the presence of like this like XOR decryption inside of a loop is usually sufficient. So then I want to find a string from car code function usage. This converts a UTF-16 code value into a string. And it's going to do that conversion on the usage of car code at. So it's basically going to find the UTF-16 character code for some portion of the ciphertext. And it's going to XOR that, so our important XOR operator, with a portion of the XOR key, which is like the key, it's the ciphertext position modulus the key length. So that's what that is and how it matches this portion of our text. And you can again see the simpler version, the more complicated version. And you see that I made some variations in my regular expression to detect both when it looks like string dot from car code and when it looks like the string class calling the object from car code. And this is what it looks like in the YARA rule. So YARA rules are a really cool, really powerful tool that can basically be run to match on files. It's designed for finding malware. It's got 3 sections, a meta section, which it's optional, but it's useful to describe like specifically what it is you're looking for. Sometimes you put in like a hash value, like this should be a successful match. This is when it was created. This is like the campaign it was related to, etc. Strings, in here you can have regular expressions, which is what I used, actual like literal string values, which are going to be inside of double quotes. You can also have hexadecimal byte sequences, which are going to be inside of braces and will just consist of hexadecimal characters and will represent those literal bytes. And then you have condition, which is going to be some combination of attributes such as file size, some logic related to strings. It can say like one or more of blank number of strings. It can say this string located at this position within a file. There's a lot of flexibility that I don't have time to get into, but that is what a YARA rule is, and it's what we use to find bad things. When I ran this specific YARA rule about 8 months ago on VirusTotal on the corpus of like the previous 365 days of submissions, it found over 1,800 matches of this kind of malicious JavaScript. And this is demo. I basically grabbed some samples. I grabbed the 2 that you saw and then one other variation and just put it on a machine and ran YARA against it. And the syntax for that is very simple. It's YARA, your rule, the location of where you want to find samples. It is pretty fast, but if you do it on an entire file system, it will take like 20 minutes. So just be prepared for that. But it's very helpful, especially in your like incident response type situations where like I know malware exists somewhere on this file system, and you can run that against the entire file system and locate it. And then my final demo. So yeah, like I said, I think that represents most of us. So here, I wanted to try and find a way to demonstrate like what this might look like in a script. So I'll just hit. So I created a simple script, and the idea behind this is, again, there are better ways to do this. I don't recommend this being the solution, but I wanted to write a expression that would find regular expressions and then also find something that's RDOS vulnerable inside of it. So I found a particular repository that I knew to be vulnerable to regular expression denial of service. I'm doing a clone of it and checking out the vulnerable commit. And then I just want to find JavaScript files inside of it. It found 31. And then this is one of the cases where I made a design choice that, because like data is complicated, I want to describe each of the potential ways that I might find a regular expression within it. So I described equal sign, and then double quote, and then the regular expression inside of forward slashes, optional flags at the end, and then close it with a double quote. Same thing but with a single quote. Same thing with no quotes, and then colon with no quotes. So those are the different ways that I described find me regular expressions. And then it finds 77 unique regular expressions within these files. And I think some of those are not correct. I don't think this is an entire regular expression. So it's got some tuning to do. But it found all these. And then I wrote this, which is a monster. It's basically looking for the case of a character one or more times that has, an optional character or group after it, and then the character one or more times after that same character. So I'm implementing a capture group, I'm implementing a back reference, I've got a lot of difficult logic trying to find something like that inside of a group. So it's gonna look through those strings and try to find something bad, and it finds one. So the reason this is vulnerable is it looks for, nope, right here, yes, here. It looks for one or more spaces, an optional new line, and then one or more spaces. And it has to find, and then one or more spaces. And then it has to find end of input. So basically, if you've got a bunch of spaces and then you have anything after that, it's kind of like the Stack Overflow RDOS, it's very similar to that, then you can create a denial of service. So that's how you might implement something like this in a script. These are some resources. If you want to learn more, kind of depends on how deep into it you want to go, but if you're very interested in this, I highly recommend the first one, regularattackexpressions.info. They go very deep and go into a lot of the computational algorithmic science behind it. There's ways to definitely put safeguards in place for that, but again, that's the nuance of what does my application have? So for example, some of them, I think a lot of times a 3 or 5 second timeout is standard in a lot of the basically if you have an application that's implementing this, so I'm using this inside of a seam or some other basically it's a searching algorithm, then yeah, it'll implement a timeout. But if you're writing this into code, then it depends. Yeah. It depends. It's useful if you look into the code and read the context. So for one of the examples I gave where the entry was a header value, so specifically I think they put it in the cookie value, and they basically said cookie equals all those backslashes, and then they just never put a quotation. So you have to read the code to figure out what we call it source and sink whenever you're doing these type of injection attacks. If the sink is the regular expression, you have to go back to the source and see where it was, where that input began. In that case, it began in the header value. In in the Stack Overflow case, I think it was reading pages. So it was a page of large white space that made that one fall down. I am not sure what caused the Cloudflare one, but I mean, literally anything could have. So again, the answer is it depends, but it could be something like an email address. That one's probably, it's got a character limit, so that one may not be vulnerable even if the regular expression is. It's going to be case by case, unfortunately. Oh, so like looking for a malicious input, like like a bunch of pluses or whatever. That's possible. I don't know. Like I'm not on like Cloudflare's WAF team, so I couldn't tell you what rules they have and have not turned on. I'm going to guess that's not exactly a high priority rule for them, but I don't know. They might have something like that. Cool. Thank you for your time.